Today we will start from the cross-power spectrum density. For the cross-power spectrum density, we have the definition here. For x and y, okay, that is also the Fourier transform of your cross correlation. And here, x and yx, actually, you will see this is different. They are not equal. So the cross power spectrum, yes, omega, and as of yx correlate cross spectrum, they are not equal, because you can see the cross correlation. You will see the cross correlation xy now that should be equal to yx, but it's symmetric, so it's minus tau. Therefore, actually, for those two cross power spectrum density, we have the conjugate symmetric. It should be conjugate. Let's see an example. X is a random process, and theta is uniformly distributed from 0 to 2 pi. And y is y-sense stationary random process, and I have autocorrelation. We assume that x and y are independent, and with that another random process z equals the product of your x and y. Then we want to find the power spectrum. You can prove that actually x is also y-sense stationary. Okay, let's quickly review the requirements for y-sense stationary. The autocorrelation is what? Your mean should be a constant or 0, and your autocorrelation should be a difference of your time. So in this case, x is y-sense stationary, and then the autocorrelation. The autocorrelation is 1/2 cosine omega naught tau. Then you can take the Fourier transform or check the table, and you can get the spectrum. So the spectrum is, if I have a cosine in time domain and in frequency domain, they will shift to the right and shift to the left, and also the magnitude will be half of the original one. So pi over 2 delta function omega minus omega naught plus delta function omega plus omega naught. And for the y, also y-sense stationary, then their autocorrelation is e to the minus alpha tau. If I take the Fourier transform, we will get the spectrum is 2 alpha divided by alpha squared plus omega squared. Now, to find the power spectrum density of the z, we can find the autocorrelation of z first, and then take the Fourier transform. So we need to find the autocorrelation of z. So T1, T2. So that is the expectation of z, t1 times z, t2. So z1 is x t1 y t1, and z2 x t2 y t2. Remember, x and y are independent. That means I can put x in one side, one part, and y in the other part. So that is the expectation of x. And then I times the expectation of y. Since x and y are Y-sense stationary, that is the autocorrelation with the time difference. First minus the second. And also for the y, also first minus second. And you can see this is the time difference. Then we can combine it as autocorrelation of z with the time difference. So actually z is also the Y-sense stationary. Then we can take the Fourier transform to find the Pau spectrum. To find the Fourier transform, or since here we have the Pau spectrum of x and y, if I have a product in time domain, what is that in frequency domain? Convolution. So actually we have these two Pau spectrum, then we can do the convolution to get the Pau spectrum. So by the convolution, theory, and then duality. Fourier transform of Fourier transform, then we can get the Pau spectrum of z is 1 over 2 pi, and you do the convolution of your Pau spectrum of x and Pau spectrum of y. So for Pau spectrum of x, since it is a shift, it's a delta function. So I just shift to the right and shift to the left. When I have values only at omega naught and only at omega naught and minus omega naught. So this is pi alpha square plus omega minus omega naught square, and pi alpha square plus omega naught square. So you get, we cancel pi, then we have alpha over 2 as a numerator, and then the denominators are the same. Then next, we're going to talk about the random process. Through the linear system, we can really apply the random process to a system now, because we want to design an optimal filter for predicting the signals. And for this method, so far we just restrict our random process as a Y-sense stationary process. So if I consider a linear time invariant system, the LTI system, I have an input and I send the signals to a black box. Say this is a system. And then I get the output. So the output is the convolution of your impulse response and your your input X. So when we do the convolution, the H is the impulse response. This is a general form. Okay. Now we will restrict the input, the random process, as a Y-sense stationary. If X is Y-sense stationary, then let's take the expectation and see the expectation of Y. Okay, so if I take the expectation, what should we keep? Because the expectation is for the random process here. H is just, you can think about H as a constant function. So we will take the expectation of my X. And then let me write it down here. So what is the expectation of X t minus tau? That is the mean, mu X. And then we do the integration. And that is, this integration is that when omega equals 0, then I have this form. So it's mu X and times the impulse response at 0. And this should be equal to the mean Y. All right, so now you see that the mean of Y is a constant. X is Y-sense stationary. It looks like we can check if Y is also stationary. Now the mean is constant. Let's check the autocorrelation. If the autocorrelation is the difference of time, then Y is Y-sense stationary. So let's see. Now t plus tau and t. So I still take the expectation for both. I have a different dummy variables. Then let's combine it together. We can take the expectation inside the integral. So if it is inside the integral, I have H, R, H, S, then expectation T plus tau minus R, and then X, T minus S, ds, dr. And for this one, first minus the second, I have, because this is the correlation, autocorrelation for X, and we know X is Y-sense stationary. So this should be the autocorrelation of X, and the first minus the second term, tau plus S minus R, ds, dr. And you see that there's no time here, so that is the autocorrelation of Y of tau. Then we have the autocorrelation. Take the Fourier transform, we get the power spectrum. So here's the power spectrum. And then how do I simplify that? So Ry is here, and times exponential. Then let's change the variable. We have tau plus s minus r. I want this just be, say, u. Okay, so that u equals tau plus s minus r. The overall integration, it becomes h of r, h of s, and rx u exponential to the minus j omega. Tau becomes u plus r minus s ds dr du. Okay, so here this one becomes u, and then tau will be u plus r minus s. Then we can separate. First, for h of r, and we have exponential e to the j omega r. And for s, h of s, exponential to j omega s ds. And then the last integral, the autocorrelation of x times e to the minus j omega u du. First is the impulse response h of omega. And how about the second one? I don't have minus sign here. This is the conjugate of your impulse response. And the last term is the power spectrum of x. So actually for y, the power spectrum of y, that is the magnitude of your impulse response squared times the power spectrum of x. Let's see the example. I have a y-sense stationary x, and we have the autocorrelation r is a sinc function. So suppose x passed the LTI system, and I have an input-output relationship. I need to find the autocorrelation of y. How do we find the autocorrelation? Many ways. One that we can use is that we know that the Fourier transform of the autocorrelation is the power spectrum. So if we can find the power spectrum of y, then we can take the inverse Fourier transform to get inverse Fourier transform to get the autocorrelation of y. Or from this formula, consider the linear time invariant system. If I can get the power spectrum of x and also the impulse response of this system, we can also get the power spectrum of y directly. So let's see. If I have a sinc function, let's see. If I can get the power spectrum of x, then through this relationship, we can get the impulse response. So then we can get the power spectrum of y directly. So for the sinc function, WT. If I take the Fourier transform, actually that's pi over W. It's a rectangular function. Therefore, the autocorrelation of x, we say it is a single function with pi tau. So WT becomes pi tau. Then when I take the Fourier transform, we'll get pi, omega becomes pi. Rectangular omega. No, W becomes pi, so 2 pi. And then if the Fourier transform of autocorrelation is, well, this, that means the power spectrum is either 1 or 0. When omega is between minus pi to pi, then it is 1. Otherwise, it is 0. Then let's see the system response. For the system response, according to that equation, the system response is 3, here have 3, minus 3 and 6, and denominator 2, 2, 4. So 3 j omega squared minus 3 j omega plus 6, denominator 2 j omega squared plus 2 j omega plus 4. That's equal to 3, 2 minus omega squared minus j omega. 2 minus omega squared plus j omega. So let's see the magnitude square of this system response. That's 3, 2 minus omega squared minus j omega times 3, 2 minus omega squared, and then we plus j omega. Similarly, in the denominator, first is plus j omega, and the second one, because we take the magnitude and square, so 2 minus omega squared minus j omega, and we get 9 over 4. Alright, then we can find the power spectrum of Y. The power spectrum of Y will be the magnitude square of the system response. That's 9 over 4. And then you take the inverse Fourier transform. You got the autocorrelation. Sinc function, the pause, and then if I take the inverse Fourier transform, then I will get the sinc function. Okay, if I have a pause, then in Fourier transform is impulse, the sinc function. If I have sinc function, then I take the Fourier transform or inverse Fourier transform, I'll get the pause. Now the last part is that how about the cross correlation function through the linear time invariant system? And we still talk about the Wisen stationary random process. And here we have a joint Wisen stationary. So two random processes, X and Y, they are joint Wisen stationary. We say they are joint Wisen stationary if X is Wisen stationary and also Y is stationary. Their cross correlation should be a function of time difference. So if X and Y are joint Wisen stationary, and you see their definition, the cross correlation will be first it will be X, and second will be Y, and you can see the first minus second, you get tau. So if I reverse the X and Y, here YX, I should have Y t plus tau and X tau. Then I will get minus sign. Let's prove. Let's just prove it. If I have YX, that's minus tau. That means in the expectation, first should be Y, second should be X. T minus tau times X or T. In that case, the first one minus second one, I'll get minus tau. We can change the variables. So T minus tau become T prime. Then we have X. This one becomes T prime. T prime means T minus tau. So T equals T prime plus tau. So T becomes T prime plus tau. So X, here we have T prime plus tau. And your Y is T prime. And so that's why this is the auto cross correlation of XY tau. Then we can take the Fourier transform. Then we get the cross spectrum density. Here's the definition. We have XY, so here is XY. If we have a YX, there'll be YX. And they are not equal. They have these relationships. Let's prove it. So if I take the Fourier transform of the cross correlation of XY, let's see what happened. By the definition of the Fourier transform, we have our XY tau exponential minus j omega tau d tau. Let's change the variables to get our YX. We know these relationships. Okay, if I change it reverse X and Y, then we get minus tau. And here we have e to the minus j omega tau d tau. Let's have tau prime equals minus tau. And then d tau prime will be minus d tau. So we'll change that to tau prime. This is the integration or YX tau prime e to the j omega tau prime d tau prime. Since there's a minus sign, so I change this, and also a minus, so I change that back. Okay. Then we get this yx conjugate omega. And here I have x to pass a LTI system and to get y. Then the cross correlation. Here's the cross correlation. Let's prove this. So what is the cross correlation of yx? That's expectation. Y first will be t plus tau, then x of t. And we know that we sent the x to an LTI system to get y. So how do we express y? Integration of x. We have y will be t plus tau, so we have t plus tau minus say r, h of r dr. And then we put the expectation inside the integral. xt plus tau minus r hr dr. And this term is the autocorrelation of x first minus second. So we'll get x r of r minus first minus second over r minus tau. But we can switch, well, either way, because we can switch the order. Then here we have rx tau minus r hr dr. And then definition for the cross power spectrum density. If we switch, okay, then we'll get the conjugate. So let's see three examples for this. X is Poisson stationary, and we have the autocorrelation. We have a system response. We want to find the following terms. So if the autocorrelation is exponential, we can definitely get the power spectrum. So if the autocorrelation is e to the minus tau squared over 2, then when you take the Fourier transform, you'll get square root of 2 pi times e to the minus omega squared over 2. That is the power spectrum of x. So the cross power spectrum xy will be h conjugate times the power spectrum of x. Oh, and then we have that here and here. So finally, that's square root of 2 pi times e to the minus omega squared. And then you can take the Fourier transform, inverse Fourier transform. You get the cross correlation. Then how about the power spectrum density of y? The power spectrum density of the random process y we know this should be the magnitude of omega, the system response square of power spectrum of X. And then how do I get the power spectrum of Y? We have the Fourier transform. Wait, we haven't got the power spectrum Y. So here we have H, and then power spectrum of X. So we have it'll be square root of 2 pi and exponential to the 3 minus 3 omega square over 2. And we have a Fourier transform pair, so we can get the power autocorrelation of Y. Or maybe then we can take to get the autocorrelation of Y. It'll be 1 over square root of 3 times exponential to the minus tau square over 6. Next example, x and n, I think that's a noise, are two random Weiss stationary random process, and we have the mean of x, mean of n, and x and n are independent, and then y is x plus n. We want to show that x and y are joint Weiss stationaries and find the cross correlation. How do we show they are joint Weiss stationary? First, their mean should be also a constant, and their cross correlation should be a function of time difference. So, first, we know x is Weiss stationary. If we can prove y is Weiss stationary, then the mean of y is a constant. And also, the autocorrelation of y is a function of time difference. Yeah, let's prove that first. We need to show y is Weiss stationary, because if they are joint Weiss stationary, each of random processes should be Weiss stationary. So we need to show y is Weiss stationary. So first, the expectation of y, that'll be expectation of x and n, and they are independent. The mean is 0. The mean is 0 for n, and the mu x. So this one is mu x. It's also a constant. How about the autocorrelation? Let's say T1, T2. Then we have y T1 on y T2. For y T1, that's x T1 plus n T1 x T2 plus n T2. And they are independent, so we can do one more here. That'll be x T1 times x T2. And the other term, n T1 n T2. So since x is y-sense stationary, and also n is y-sense stationary, so this is the autocorrelation of x with the function of time difference, and also the autocorrelation of n with the function of time difference. Then since they are a function of time difference, so the autocorrelation of y is also a function of time difference. Now we also need to check the cross correlation is a function of time difference. So they are xy t1, t2. So x will correspond to t1, y will go to t2. And y is x plus n. So here we have x t1 times now x t2 plus n t2. They are independent and the mean of n is 0. So we have expectation of x t1 and x t2. Okay. Since here we have x in this cross term, and they are independent, we can have ax and the expectation of n. And since they are 0, so this term is gone. So this, you can see, this is the autocorrelation of x, and it is a function of time difference. Therefore, since the cross correlation is a function of time difference, is a function of time difference t1 minus t2, and also x and y are y-sense stationary. Then x and y must be a joint y-sense stationary. Let's just quickly go through that. Next, I have a U that's a zero mean random process. And then this autocorrelation is a little bit different. It's a minimum of either T or S. So this could be T or could be S. And then we define the random process X is related to our another random process U. So first, I want to find the autocorrelation of X. Then that's the expectation of X, T plus tau, X of T. So it is exponential T plus tau, and then the U of the exponential to the minus 2 times T plus tau. And then the X, so e to the T, U of e to the minus 2t. So let's rearrange that. There'll be e to the 2t plus tau, and then u e to the minus 2t plus tau, and u e to the minus 2t It's e to the 2t plus tau. And here's the autocorrelation of u of e to the, well, so it's the mean of t or s. So it's either this one or this one. So e to the minus 2 t plus tau exponential to the minus 2t. So there will be the minimum of e to the minus 2 t plus tau or e to the minus 2t. Then what is the answer? Because it's either this one or this one, right? So let's see. It's either e to the minus 2 t plus tau or e to the minus 2t. When will we get this answer? When tau is greater than or equal to 0. Otherwise, when tau is less than 0, we have e to the minus 2t. So overall, it should be e to the minus tau when tau is greater than or equal to 0, or e to the tau when tau is less than 0. So overall, that should be e to the minus absolute value of tau. And then take the Fourier transform, we can get the spectrum of x. So Rx is exponential to the minus absolute value of tau, then the Fourier transform is the spectrum 2 divided by 1 plus omega squared. If I send the x to the linear time invariant system in this form, send it to d over dt. And this is a linear time invariant system. Then I want to find the autocorrelation of y. So first, let's write down the equation of x and y, their relationships. Y should be equal to x plus dx over dt. Right. This means that my system response h is 1 plus j omega. And then the magnitude squared will be 1 plus omega squared. So the power spectrum of y will be h, this magnitude times the power spectrum of x. That's 1 plus omega squared times 2 divided by 1 plus omega squared. That's equal to. And then that means the autocorrelation of y, because I can take the Fourier transform, the autocorrelation of y is delta function. So if this is 2, then the Fourier transform will be like a delta function. A delta function, then the Fourier transform will be a flat, well, a constant number. Lastly, you can find the cross correlation yx. So we need to find the cross power spectrum yx. It's omega times the power spectrum of x. So we have 1 plus j omega times 2 divided by 1 plus omega squared. That's 2 divided by 1 minus j omega. Then when you take the Fourier transform, you can get the cross correlation of yx. There'll be a unit step function. X is y-sense stationary, and we have the autocorrelation and the power spectrum. And we have the theta, that's the random variable, and y, x and y, the relationships here. And x, this random process, is independent with the cosine. I want to feel weird. Where's the t? Cosine t. These two random processes are independent. So I want to find first the autocorrelation of y. So for the autocorrelation of y, that's expectation y t plus tau times y t. So we have y here. That means we get 2, because expected square root of 2 times square root of 2, that'll be 2 times the expectation x t plus tau cosine omega naught t plus tau plus theta x and cosine omega naught t plus theta let's simplify that. Since x and also this cosine are independent, so we have x t plus tau times x of t. And the rest of the term with related to cosine, here we have cosine omega naught t plus tau plus theta and cosine omega naught t plus theta. So the first one, that's the autocorrelation of x. So 2 autocorrelation of x, and then the rest will be cosine omega naught tau times 1/2. And I think we practice that a lot in the previous 2 lectures. So overall, that is they are autocorrelation of x times cosine. I need to show you that we have the autocorrelation and the spectrum. And now here is the spectrum. Let me plot here. I just give you the spectrum. Minus omega, and 2 pi over w. So if I give you the spectrum, you can get the autocorrelation. because we also need the autocorrelation here. So the autocorrelation is the inverse Fourier transform of your spectrum. And then this will be the sinc square function. Therefore, the autocorrelation of y will be the sinc square function times cosine omega naught tau. And if you take the Fourier transform, what do you have? The spectrum of y. So the spectrum of y will be, we have a cosine, right? That means I will shift to the left and shift to the right. And the magnitude will be half of that. 1/2 of your power spectrum of x, shift to the right and then shift to the left. And now if I send this y to a system, an LTI system, so if I send y to a system, but we times a cosine function, kind of like doing the modulation. Let's see if I do the modulation. Square root of 2 cosine omega naught t plus theta. Got u. And then I send it to an LTI system with the system response. Then my output is z. I want to find the spectrum of u. Well, u will be y times the cosine function. So to find the spectrum of u, we can find the autocorrelation of u. The autocorrelation of u is the autocorrelation of y times cosine omega naught t, a tau. And then we take the Fourier transform to get the spectrum. So in this case, because I have a cosine, so I shift to the right and shift to the left. Then get 1/4 omega minus 2 omega naught and 1/2 omega, and then shift to the left. So in the beginning, that's my spectrum, but I will shift to the left and shift to the right. Then it becomes and then the magnitude will be half of that. So this is my original one. And then I shift to the right and the left. And then the magnitude is half of it. Now, suppose the system response is 1 between minus omega to omega. Yeah, and then let's find the autocorrelation of z. So if the system response is 1, 0, when the omega is between, here we'll say, just say omega or w. Then we want to find the autocorrelation of z. We know that to find the autocorrelation, you can use the definition, or we know that if I take the Fourier transform, I will get the power spectrum. So if I can find the power spectrum, I can take the inverse Fourier transform. But what is the power spectrum of z? Through the LTI system, your system response magnitude square times the power spectrum of y of u. So here you have this square and then power spectrum of u. Also, this term is either 1 or 0. So I will get either power spectrum of u or 0. Then therefore, the autocorrelation of z will be 1/2 of autocorrelation of x. So that's a sin square function w tau over 2. X is a zero mean y-sense stationary, and it is y-sense stationary. Gaussian white noise. We have the autocorrelation. And X is the input to the LTI system. And we have the impulse response. And then Y will be output. I want to find the mean of Y and the spectrum of Y. To find the mean of Y, that's easier. We just follow the definition. The mean of Y, that's expectation. What is Y? Y is the output. So we do the convolution. And then we can put the expectation inside the integration. It'll be x t minus tau d tau. Zero mean. Okay, so this goes to 0. Therefore, the mean is 0. Now I want to find the power spectrum. To find the power spectrum, we know the power spectrum Y is the magnitude of your system response squared times the power spectrum of X. So first, let's find the power spectrum of X first. So what is the power spectrum of X? Do we have the autocorrelation of X. So here we have S naught delta function e to the minus j omega tau d tau. And since it is the delta function, so we have S naught. Only when tau equals 0 that I have 1, so it's S naught. And then how about the system response? For the system response, Ht, taking the Fourier transform, and well, we have H, so here it should be from 0 to infinity, e to the minus alpha t, e to the minus j omega t. And then this, when you do the, if you do the integration, or you can check the table, there'll be 1 over alpha plus j omega. Well, so apparently then we'll get the power spectrum of Y. So it'll be S naught times 1 over alpha plus j omega, and then 1 divided by alpha minus j omega. Because the magnitude square, that means H times the H conjugate. So you have S naught over alpha square plus omega square. And then you can check the Fourier transform, Fourier table. Then we have the autocorrelation of Y. That's S naught divided by 2 alpha, e to the minus alpha, and absolute value of tau.